part of my report for correlation and regression using the R Studio. So now I'm going to report about how to do the Pearson's R correlation coefficient um, um, analysis using R. So the Pearson's, or the correlation coefficient of Pearson's correlation, is actually represented by small letter r. So for Kendall it is tau, and for Spearman it is rho. So what is actually the Pearson correlation is, and when do we use it? So Pearson correlation is actually a statistical measure of the strength of relationship between the two quantitative variables. So the variables must be continuous in order for us to do the analysis of Pearson, or the analysis of correlation using the Pearson's R. It is a common tool that actually describes the relationship without stating the cause and effect of the changes between the two variables. So R, coefficient value of close to -1 or +1, indicates a strong linear relationship between the two variables, and a zero value of R indicates that there is no correlation between the two variables. So in order for us to do the Pearson's R correlation analysis, we have to meet few assumptions here. So the first one is, of course, the random samples. So the samples must be randomly selected. And of course, this is not new to statistics, because manipulated samples due to non-random sampling is actually questionable in terms of accuracy. So yeah, the samples must be random. So another assumption is that x and y must be continuous. So the variable x and y must both continuous or numerical in natures. Otherwise, we have to use either Kendall or Spearman if we're going to use if one of our variables is not a continuous type or quantitative type of data variable. And then measurement should be on interval or ratio scale. So when we say interval, the measurement falls below 0. So for example, temperature falls below 0. So this is considered negative temperatures. And the nature of measurement for this type of variables is interval. So the ratio, however, is actually a scale where a variable do not fall below 0. For example, age and height are variables. These are the types of variables that do not fall below 0, because we don't have the 0 age. And also, the data must contain paired samples and independent. If the data contains missing values, then we must remove this data. So I have already showed you the codes on how we can remove the missing values from our data sets. And then, yeah, the variables should be at least normally distributed and showing a linear relationship. We can use a histogram or a scatter plot to visualize our data to ensure that we met these two assumptions here: the normality of the distribution of data and the linearity of the relationship between the two variables. And finally, Pearson correlation is greatly influenced by outliers. So outliers are the observation that go far beyond the normal distribution of our observation in our data sets. So normally it is a lot easier to identify if we have outliers in our data by plotting our data first using the scatter plot. So later we can have a look on how this outliers looks like in our scatter plot. But if we have the outliers in our data set, then probably Pearson's correlation is not the right method we have to try with doing the correlation analysis. Now, before we begin the Pearson's correlation analysis, as I have said earlier, we must all satisfy these assumptions that I have just said. And we can do that in A. Actually, we must visualize first our data using the scatter plot to see if there's a potential relationship in our variables. So we can do that. We can use the plot function, and inside the parentheses is the two variables that we want to have a look on the relationship. So they are separated by tilde sign, this one, tilde sign, and then this PCH value of 16 is just an abbreviation of the vector points for our and then for our x-axis over here we can put the calories, and for our y-axis we can put this sodium variable. So it's just the name or the legend of the x and y axis. Now we run this one. If we run this one, okay, that's right. You get this error here. Sorry. Sodium. Okay. So, as you can see from our scatter plot on the right, the data point seems forming a pattern. This might indicate a relationship. So we can go further to run the correlation analysis. And of course, we don't see any outliers in our data set or in our scatter plot, rather. So if you want to change the point abbreviate from circle to the rectangle, we just have to change this PCH value from 16, this one, from 16 to 24. And if I run this one, so you'll see that the rounded data points are now changed to rectangular form. Now let's say we satisfied all the assumptions per person correlation. So we are now ready to run the correlation analysis using the core.test function. And within the parentheses is the tilde sign again. Yeah. Then it will be followed by the y variable, sodium first, and then plus sign, separated by plus sign, and then followed by our independent variables, which is the x variable, sorry, the calories. Then we type in the data. This is the default one, the small letter D, and then followed by equal sign, and then the name of our data set, which is the big letter, the capital letter D on it. Then we have to specify the method we want to use, and for this analysis we want to run the Pearson correlation analysis, of course. So we type in the Pearson. Let's run this one, and the output for our correlation analysis is displayed on the terminal window over here at the bottom. So we can also run the correlation analysis using the command over here, this one's, instead of using that one over there at the top. So this will actually going to yield us the same result. Okay, so as you can see from our correlation result, the value of the D distribution, as well as the degrees of freedom. So we have the 43 over here for degrees of freedom. And we're actually interested in the value of the p-value to decide whether we have enough evidence to reject or accept the null hypothesis. And as you can see, we have an alternative hypothesis over here. So the the alternative hypothesis stated that here that the true correlation is not equal to 0. So another useful information we can find in here is the two values of confidence intervals. Here, 95% confidence intervals, and then below that are the two values of them. And this means that the value, the true value lies beyond our set of two confidence intervals. So the true value lies beyond these two calculated confidence intervals. So our correlation test result is equivalent to 0.8489 with a p-value that is lesser than the conventional 0.05 alpha level. Therefore, we can conclude that there is a significant relationship between the sodium and calories. And of course, we can also change the confidence interval by running this command over here. Let's say we want the confidence interval of 0.90 or 90% instead of using the default 0.95 or 95% for this analysis. So if we want to do that, we can run it, and then there's not much changes at all except for the values of the two confidence intervals in our result over here. That means the true value that we are looking for actually falls below this, between these two values of the confidence interval here. So by default, the correlation test runs two-tailed analysis. That is why the alternative hypothesis here states that the true correlation could be above. See, it's not equal to 0. It could be above the 0 or below 0. This means that we have two directions, which either a positive one or a negative association. And that means that's two-sided analysis. So alternatively, we can run one-tailed analysis of correlation tests, and the alternative hypothesis will basically going to add greater or lesser word in here. So basically, we just have to run similar code, except we write in the in alternative, then equal sign, then followed by the less word with the double quotation mark in it. And if we run this one, we can see that the correlation this time should drop a negative correlation since it is lesser than 0. So if you want to run a one-sided analysis with the testing of the true correlation greater than 0, we just need to change the word less in our code here to great. So that means that we are running a one-tailed analysis, and we're looking for a true correlation that is greater than 0. Okay, so as the one who's working with statistics, accuracy of the results is actually very important. So it is always a good habit to not just rely on the result of the correlation test that we just have performed earlier. So to make sure that our data have met the assumptions of the normality, we must have a look at the residuals of our Pearson correlation analysis. So what are the residuals? Residuals are actually the errors in our correlation analysis. But unfortunately, the core test function doesn't apply the residuals. So we have to use the LM function, which actually check the linearity of the regression. To do this, we can use the code LM, and then within the parentheses our two variables, so sodium and a calorie, separated by the tilde sign, and then the default data word here with a small letter D, equal sign, then the name of the data set, and then we will create a data frame for this instance. We will call it model, and then this equal sign here will simply pass the the resulted output of this function here. Next is we have to run this one. Next is we have to create a variable x and use the residual function here to calculate the residuals or the errors on our model. So let's also run this command. Now, what is the assumption for the residuals? The answer is the residuals are assumed normally distributed, so errors must be normally distributed in our data. So if the residuals are not normally distributed, then we have a problem on our current model. So to visualize this distribution, there are a few tests that we can use. This could be in the form of histogram, or QQ plot, or density plot, or a Shepard-Wilk test. Again, the main goal of using this test is to check the residuals. To check the residuals is to provide a proof whether the residuals are in fact showing normality of the distribution of the data. To run histogram tests of the data distribution, we have to access the R companion. This means that histogram is within the package R companion. Otherwise, we'll get an error if we don't load it up in our package library. So if you haven't installed yet the R companion package, you have to do that before you access that with the function library. So I have already installed the R companion library. I want to access that with the R companion library. Sorry. And now to plot the residual using histogram, we can use the function plot normal histogram, and within the parentheses is the x that contains the linear regression command for our analysis of the residuals for our model. And if we hit run, you can see here on our data in gray bars. So the gray bars are our data, although not perfectly following the blue bell-shaped line over here. So it is actually showing a normality of the distribution. It depends on how do you interpret it as a researcher. Although that still depends on the of course the interpretation of the interpreter. So as a researcher, we have to ensure that we actually visualize the residuals well, and not by looking at the histogram alone. So it's a good habit to do this in practice, but not just looking at the histogram. We can also use the QQ plot or the probability plot to check the normality of the distribution of our data using the function QQ norm, and then within the parentheses is the data frame we are looking with. This is very useful when determining if the residuals follow a normal distribution. If the data, if the values of the data that in the plot follows a roughly straight line at a 45 degrees angle, then the data is normally distributed. So look. So let's run that code, and as you can see, the residuals are somehow forming a straight line pattern over here. We can also use the function QQ line, so we can clearly see that there are few data on top of it that seem to deviate from the lines. So this indicates that the data seems not normally distributed at this time, but majority of the data points are actually following the trend line over here, so we can see that it is in normal distribution. Now, we can also use the function plot. So this one will result into the residuals of our model. You can see from our density plot over here. Run this one. So you can see from our density plot over here that the line is forming a bit of a bell shape with a bit of skewness on the right. And we have to remember that the perfectly normally distributed residuals is actually represented by perfect bell um, shape pattern. But of course, in reality, you cannot get that really perfect one. So depending on the what type of data, we may decide not to perform a transformation on the data to ensure that the residuals become more normally distributed. And finally, looking at the uh, uh, histogram or a QQ plot or density plot sometimes still bring us another second thought about our own interpretation. However, using the Shapiro-Wilk test, the result would be more statistically represented because the output now involves the testing of the p-value. So if the p-value, let's run this one. So if the p-value of the Shapiro-Wilk test is greater than the conventional alpha level of 0.05, then we can conclude that the residuals are normally distributed. So just type in the Shapiro that test over here, and then within the parentheses is the name of the data frame. So if we run that one and we get the p-value of 0.28, which is greater than 0.05, therefore we can conclude that the residuals are normally distributed in our data. Now, if you want to run correlation analysis using Kendall, you can use the function from line 242 to 244. As you can see, we have a Kendall tau result of correlation of 0.65, similar with the experiment correlation. We can run the command from 251, lines 251 to 253 as well, and just type in the Spearman method over here. And if we run this one, it will yield another result. Sorry. We'll give it. All right. There's an error in there. Okay, I'll change this one to data. Sorry. And if we can see that the Spearman's raw correlation coefficient is now equivalent to 0.82. So for our for our Spearman it's 0.82, and for tau it is 0.64, and for Pearson's R it is 0.84 correlation coefficient. Now, a simple, so what are the assumptions for the Spearman correlation? So Spearman is a non-parametric version of the Pearson correlation. So what does it mean? So it means that the approach of analysis is the same as the Pearson correlation, but the variables involved doesn't have to be both continuous. So in fact, the two variables is either ordinal or continuous in nature. And of course, the scale of measurement for Spearman is the same as the Pearson correlation, but it must be, of course, interval or ratio. So it is assumed that the samples, when we're doing the Spearman, should be random as well, and the data must contain a paired samples. Otherwise, if we have missing values in there in our data set, then we have to remove it before we do the analysis. So we can go back to my question earlier about how do we use the Spearman over the two correlation, over the other two methods of correlation, especially the Pearson correlation. So the answer is to always check the scatter plot first before doing the analysis, because the Spearman determines the strength and direction of the monotonic relationship, and the Pearson's correlation measure the relationship, the linear relationship rather. So when we say monotonic relationship, so as one variable increases and the other increases too, and the vice versa, and that appears that uh, uh, following and not following a nonlinear straight line or linear relationship, because it is in a not constant rate of change. So in this case, instead of using the Pearson's R correlation, we need to use the Spearman to measure the strength and direction of the monotonic component of our data. So that's it for the Pearson's R correlation, and the next report will tackle the simple linear regression. Thank you for listening.